Hey everyone, welcome to the stream. Sorry I didn't stream the other night. I've been doing a lot of extra hours at work, and we got a major release coming out, so by Tuesday I was just really too tired. Actually, to be honest, I'm still really too tired to stream, but I thought I'd just put in a little bit of time because I just wanted to share something with you guys. So yeah, basically the last couple streams we were focusing on trying to fix that bug in Spike where the platforms were not showing the missing parts of the platforms, and we were getting actually closer. We were focusing a lot on the shift register, but then actually after the stream last Thursday, I guess a week ago, I spent some time looking more carefully over the trace and trying to understand what was going on, and I got the impression that the problem would actually be related to the interrupt request handler, the IRQ handler. Hey, what's up, Michael C? So yeah, like I was looking at the IRQ because what I noticed was that here's what became apparent to me. I was looking through my trace and I noticed that when we look here at the flags, I'm just gonna, yeah, here. So this is like basically all the flags in the processor. You're gonna notice the I over here. And I is basically interrupt enable. And the way it works is that when interrupt enable is low, so when it's 0, which is lowercase I, it means that we will be able to receive IRQs and process them in the CPU. And I noticed that I was low for all of the top of my trace, and then at one point it became high. And then it remained high pretty much till the end of my trace. So now I was looking at that and I was like, wow, what's going on here? And turns out that, for example, at this moment here, and now I've marked up my trace. This is me when I was looking at it. Wait, why does interrupt mask I get set to 1 after this RTS? Oh, because this is when we end up handling the IRQ. So the problem is that RTI resets I. Is that wrong? So this was my question to myself, and basically, at the same time that I was looking at this, I had Malban, who is the author of the V-Day emulator. He watched my stream and he posted on my last video here. He said, just watched parts of your video. I'm just gonna zoom in a bit. And he says, Spikes draws its lines cool. He says, haven't seen drawing like that anywhere, which would make sense since it's the only one that's causing me problems, right? And he says, since I don't know your code base by heart, I might be wrong, but I think the gist of your problem is not the shift reg, but the via generating interrupts. And he says, and this is what's interesting, he says the blank in one horizontal line is set when timer 1 expires. So then he says, then a T1 via interrupt is generated, and within a short interrupt routine, 4 lines of code at 072E, the shift reg is cleared. So what he's basically saying is that when they draw the lines, they set up this timer 1 for a certain amount of time to draw. It's kind of like, it says, okay, I want to draw a line, and it uses the timer interrupt to say kind of like, call me back, like keep drawing, and then call me back in this much time so that I can stop drawing. And that's basically what the interrupt routine is supposed to do by setting the shift register, by clearing the shift register. Because the way it works in the Vectrex is that the shift register, you put in a pattern in there, and that's the pattern of the line you draw. So if you put all ones, it'll just draw a solid line. If you put ones and zeros, it'll be like a dotted line. So you can make all these patterns because it's actually a barrel shift register. So like it basically keeps rotating its bits, and that's what drives the blank. The blank is basically the part that says whether or not the beam should be on or off. Right, so these all go together, and what he's saying is that when the interrupt service routine gets called, it turns off the drawing by setting the shift register to 0. And then he's saying, he kind of surmised quickly by looking at my code that I wasn't handling interrupts properly, which isn't the case. And so we had like a bit of an exchange there. But in the end, what he basically kind of clarified at the same time that I was looking at this was that this bit of code right here is that very short, 4 instructions that he was talking about. So basically there's a jump to this here, and then over here it clears the shift register, as he was saying. And then it puts 127 into B and stores it into the interrupt enable. So, and actually, what does he do with this here? I actually don't know why it stores. What does this do again? Oh yeah, 7F. This means to turn off via interrupts. That's actually what it means. So this basically is a 0 followed by all 1s, and that basically says because the top bit, bit 7, is do I enable or disable any of the remaining 7 bits. So in this case, it's the top bit is 0, so it says I want to disable all the other bits. So this turns off all via interrupts. And the idea there is that it's going to remain like that until later on when the processor says, okay, let's enable that timer 1 interrupt, which happens here. You see, enable interrupt timer 1. So, okay, great. Now the problem is that I would return from interrupt, and then I would suddenly be 1. It would remain 1. Hey Pyro, how's it going? And so I thought, okay, that's weird, you know, that it remains 1. And I was looking over my code for that, and so this is the CPU, okay? This is like, execute instruction. And in here, we receive a bool that says whether the IRQ is enabled or not, and also FIRQ. But let's focus on IRQ. And the idea there is that when we're waiting for interrupts, so that's exactly in the case here, right? So we're waiting for interrupts. Go about here. I'm gonna try wrapping. No, that's not good. Sorry, it's because I zoom in to try to make it a little bit easier to read, but it doesn't always help. For me, anyway. Yeah, here. Okay. Right, so I was low, and then the VIA generated a timer 1 interrupt. We don't see that in the trace, but what we do see is that we're about to handle it, and that code happens here. So we're not actually waiting for interrupts. This comes from if you use a specific instruction, but what's going to happen is we're going to come down here. If IRQ is enabled, and that interrupt mask is 0, so this is specifically that case, then this was the code I had. And this code is code that I had put together back when I was working on the game Bedlam. Oh, hold on a sec, guys. I'll be right back. Yeah, sorry about that. My son was calling me. Alright, so so interrupt mask. So we get in here, and so what I was doing, and this is what I had understood from reading a few different documents, is I would first set the interrupt mask to 1, saying like from now on, nothing can interrupt us because this is not an interruptible interrupt. And then after that, we push the CC state, and what that does here is it pushes the state of the registers of all the bits of the, of the flags. So you can see that here, and you can pass a true or false whether it's entire or not. That's basically that's an actual bit in the flags register. Do you want to set it on or off? And then after that, we push all of these here, including the CC. So that was cool, right? And then after that, we read the IRQ address, like the interrupt vector. We increment the number of cycles, and then that's it. We continue. Well, as it turns out, like at least in Bedlam, it seemed like this was the right thing to do because the interrupt mask would be, what's this again? It would go to 1. Yeah, I forget now. Something about and it's been a long time, but something about Bedlam, it would want the interrupt mask to remain 1 after it returned from the IRQ handler. And if I didn't do that, then Bedlam would like after one round of Bedlam, we would get stuck and we could not play a second round. And so that's why I had put it this way. But it turns out that this is actually not correct. And so one of the documents that I have here, I'll be honest, it's like not super clear. You know, all the docs that I read, none of them are extremely clear about what's supposed to happen, but it's sort of clear. So for example, here for the normal maskable interrupt, it says, after accepting a normal interrupt request, the processor sets the E flag, so that's the true that I pass in here, saves the entire machine state, and then sets the I bit to mask any further interrupt requests. Okay? So technically speaking, this is what we want to do. We want to, you know, the first two steps are in push CC state. We want to set the entire flag to 1, then we want to push all the state, and then we want to set the interrupt mask to 1. And in a way, this kind of makes sense, right? Like, what it means is, well, I mean, I guess it depends how you look at it, but if you look at it this way, it says, when my, whatever interrupt flag I set, when my IRQ happens, when it's over, when we RTI, I want it to go back to whatever state it had before, which means if the interrupt mask was 0, which it had to have been, right, since we came here, it'll go back to being 0 as soon as the IRQ is over. Now we can continue to receive more interrupts. And that kind of makes sense, and it is what the documentation is saying. I mean, another way of looking at it, which was what I had before, was saying, when interrupts are enabled, as soon as it is handled, then you need to tell the CPU, I would like to now handle interrupts again. But maybe that makes less sense, you know, so I don't know. So anyway, the thing that kind of puts me off here in this doc is here. After servicing the original interrupt, the user may clear the I bit to allow multiple level normal interrupts. Which I find really strange. I think, like, what is it trying to say here? See, for me, when I read this, I think, well, it says after servicing the original interrupt, the user may clear. I guess what it means is during the interrupt service routine handler, if you wanted to allow another interrupt to occur, since it's forcibly set to 1, you could yourself clear it. I think that's what it means during the interrupt service routine. So anyway, Malban, when I pointed out to him, he just kind of said, yeah, I don't know, you know, it's whatever. So anyway, just this one small change, just making sure the interrupt mask goes down here, fixes spike. And it fixes it because as soon as we are done our interrupt handler, the I goes back to being enabled. So we can now receive interrupts again. And that's going to be necessary for, like, you know, the following lines. So just to show you what that looks like, I'm sure everyone is dying to see spike work. All right, so here's spike. Just stop my music. And there you go. So now the game is actually playable because I can, like, see where the platforms are missing, right? Pyro says, isn't that just in case you have more interrupts while executing the first one, which are disabled? Yes, that exactly. That's what I think, Pyro. I think that comment was, but see, it kind of threw me off the first time when I read it because I thought it meant what I thought, how I read it, and maybe you'll see what I mean. I read it like after servicing the original interrupt, like after the interrupt is over, then the user may clear the I bit to allow, let's say, another interrupt. That's how I thought it the first time, because I thought, you know, if it remains and, you know, high after the interrupt handler, you'll have to yourself clear it for another one to occur. But no, I think you're absolutely right. You know, now knowing that it's supposed to be set the other way, and also there's certain key things in here that says after servicing the original, so the first interrupt, the user may clear the I bit to allow multiple level normal interrupts. So an interrupt that gets interrupted by another one, right? So that now makes more sense. But yeah, so here we are, and this is great, right? Like I actually was able to play the game, and it's pretty fun. It's a bit of a weird game, but yeah, it's like the only real platformer on the Vectrex. That's what I find kind of interesting about it. And it's got that cool 3D perspective, and it's a little bit like, I guess, a bit like Donkey Kong in some way. It's got this weird thing about moving the ladder. I don't really understand the moving of the ladder, but looks like you can stay on the ladder. And you see, once you're on the ladder, you can't move it. So that's kind of interesting. Those bows there, those freeze the enemies. Oh yeah, and you can kick in midair too. It's pretty impressive, like the amount of control you have. Okay, so here's the thing, Michael C. Now I fixed Spike, but I've broken Bedlam. I'm back to having Bedlam not work. I'll show you what I mean. So this works, right? So if I grab Bedlam, so I'm just gonna fast forward, and I just want to die. So this, like right now, the game works. Okay, I can fire and all that. But let's say I let myself die. I'm just gonna fast forward through here and lose another life. Okay, now it says end, right? So back to the title screen, I press go to play, and we're stuck. There's nothing I can do to keep it, to have it proceed. And this is a game that uses IRQs as well. So there's, you know, I guess I fixed it the wrong way. You know, if the spike fix is correct, which I think it is, then what made this one work was incorrect. And if you know, if we watch my old stream, hold on a sec. Yeah, if we watch my old stream, that like you'll see me having fixed this by doing this, putting the interrupt mask above here. Probably what it is that there's something else in Bedlam that should be setting the interrupt mask to low. Okay, so this will actually, now this will go back to being broken. See? But if we go to Bedlam, if I could type, and I'll fast forward again. So now, if I continue, see now it works. So yeah, so there you go. So, you know, I think this is correct. I think that, you know, the real fix is to do this here, and I think this follows the documentation. So this is the right fix as far as I'm concerned. And I need to fix Bedlam. So I'm back to fixing it, which would be kind of funny. If you were to look at the at my episode list, at one point you'll see a few of me fixing Bedlam, and then later on you'll see a few of me fixing Bedlam again. As for compatibility, Michael C., it's true, I haven't actually revisited my compatibility chart in a little while, and I probably should. You know, once I fix this Bedlam one, probably that'll fix a few other ones. But it's pretty good. Let me see if I could, where is it again? Is it here? Oh, no, it's the wrong one. I think it's here. Compat. Oh no, it was the other one. Yeah, here. Oh yeah. I think it'd be easier to just look at this in the browser. Hold on a second. I thought there was a way to preview in browser. Nope. I forgot all my shortcuts. How does this one work again? Alt P? Control P is that. Command palette. Control Shift P. Okay. And then preview. Oh, okay, whatever. So this is my my current compatibility list, and the way I separate it is commercially released ROMs. So for all of these, I'm looking for a status of great here. So yeah, so you see, like, actually now see Bedlam was no longer going to be great, but yeah. Berserk, Blitz, Clean Sweep, pretty much all of the, I had marked all the commercially released ROMs as great. Spike was in there, and I had said great because I actually didn't realize that Spike was wrong. I didn't really know this game, so I just thought, oh, looks good, but turns out it wasn't. Now it'll be correct. Then after that, while there's some light pens, I haven't done any kind of light pen emulation, like with the mouse or anything, so I don't really care. 3D Imager, I don't have one, so I got something working sort of, but it was not that interesting. And then I have a bunch of, this commercial unreleased ROMs. I think Dark Tower is working great now. There's a couple of other ones that seem to work. Probably these are fine. Like Tour de France, I think is great now. I don't really care about these ones. And after that is a whole bunch of homebrew, and I haven't really tried most of them. I'd have to go through. The audio ones, I think we could now agree that they work because I think my audio implementation is pretty good. So yeah, I'd have to kind of go through all of these homebrews and see how they play. But it's kind of tough because, I don't really know what it's supposed to look like. I'd have to play them on, I guess, a good emulator to compare. I guess that's something that could happen. But I'm just glad that at least the commercially released ROMs seem to be working. I think if I fix Bedlam, that might fix other games that might depend on the same kind of thing Bedlam depends on. You know what I mean? And it's possible that this fix for Spike may affect another game. I don't know. So yeah, that's the answer to the question of compatibility. So I'll have to do a pass on that at some point. Okay. So I think I just wanted to commit this here. So I'll say make sure to set interrupt enable I after pushing CC state when handling normal IRQ. And I'll say fixes Spike but breaks Bedlam. All right. So let me just come here. I don't know why I keep these logs, but I did mark them up, so maybe it'll be useful at some point. I want to try now taking a look at Bedlam again. But maybe now, with a bit more experience and my emulator having less bugs than at the time I wrote it, maybe we'll be able to see what's going on in Bedlam. Okay, so let's do a trace. I think I'd come up with a little regex to help me find something like this. And match case. Okay. So here's a place where we do something that brings RTI, sorry, that brings I to be enabled low, and it's actually this RTI instruction. So this must be the interrupt handler. Is it? RTI here. Yes, I think this was the game that used the interrupt handler to actually do the drawing. So there was actually a very long interrupt handler. Let me actually put a breakpoint in here. We're gonna do a continue. Interesting. Okay, I have to restart it. So it looks like what happens is we get in this infinite loop, which is why it kind of freezes. We're getting in an infinite loop because we just keep saying, "Oh, I got an interrupt to handle," and then that just loops over and over and over. And it looked like we were reading the wrong value for the interrupt handler somehow, which is kind of strange. Okay, it's not used for drawing. Okay, so here we are. My PC is 129. So we're at instruction 81. So I'll set to to break into the debugger. Just want to see what we're looking at here. Let's print out the last 100 instructions. Okay, so we're just in the process of, oh, we are actually playing with the interrupt flags here. What are we doing? We're actually reading the interrupt flags. And checking if one of the bits is set. This might be the timer code. Yeah, this looks familiar. Let me see. Yeah, it's okay, it's the wait recal function. So in the middle of doing that, we got an interrupt. CBF8. CBF8. I think that's the... So why didn't I see CBF8 in the PC when I was reading the interrupt vector? Odd. I'm going to try this again. Just want to double check because it doesn't seem to make a lot of sense. At least this time when we debug, we have audio. So it's stored at FF8, that's true. So we read 16 from there, and that just puts our PC. You know, I think what's happening here is, could it be optimizations? It always drives me crazy. No, nothing's changing. Let me see if from here, yeah, see, totally different. So my debugger is lying to me. That's useful. And if let me try something else. don't know why sometimes the optimization settings don't work for Visual Studio. What has seemed to work though is disabling optimizations at the file scope level. So if I come in here and say optimizations disabled, like that. Now I wonder if this will actually even run. There's most of the slowdown happens in here, especially with there's no inlining. I might need to put on inlining. We'll see. Oh, it's okay, not too bad. Just need to get my debug symbols. Okay, that's better. Okay, so we're at F1A0 in this case. And we will read CBF8. Hey, Danny Fritz. How does a vector display draw filled in lines like that? Curious what filled in lines like, oh, do you mean all this here? So that's not actually the vector display. Excuse me. The vector display is actually just drawing what you see, the text. And this thing is an overlay. So, because on the Vectrex, which it was black and white vector display, oh, like the big lines that move to the center and kill you. Like those kind of star things. I guess they're just drawn like, you know, lots of little vectors. You know, I suppose that once the vector beam is, you know, drawing a bunch of lines that are very short and close together, it can do quite a lot very quickly. So I think that's how they ended up doing that. Oh, okay. Talking about the fast forward, because when I'm fast forwarding, you're seeing like a bunch of frames worth of renders in one shot at a time. Okay, I understand. Sorry, I thanks Pyro for clearing that up. But yeah, so I think that's what you're referring to, right, Danny? Honestly, my fast forward is not very smart. You know, like I just basically all I do is when I fast forward is feed large delta times. And because I do that and everything is time based, when I have a large delta time, I just basically process way more CPU instructions and then process way more lines to render in one shot. Because the thing about the Vectrex, it's not like when I did fast forward on the NES emulator, it was different because on typical and regular consoles, there is a concept of a frame, right? You've got a raster display and it's rendering at 60 frames per second or whatever. So, you know, you've got 60 frames per second. And there's this whole like notion that, you know, we're drawing a frame. But for the Vectrex, there's no such notion. There is no frame. It's just, you know, executing instructions and moving a beam. So there is a function in the BIOS that you are supposed to call as often as possible to reset your beam to the center of the screen. And you can kind of think of it as a frame, but it's really not. So it's a bit different trying to do fast forward intelligently. Like I didn't really have a better way than just trying to eat up a bigger chunk of time. So that's why you get like so much stuff on the screen at once, because it's never supposed to be like that. And because I'm not able to simulate the decay of those quickly enough for you to, you know, not see them, since it's all happening in one frame. Okay, so CBF8 is the interrupt handler. And then we will run this until an RTI. And then the question is after that. So let me go back to my trace. Oh, nice, Michael C. That's really cool. Were you, I think you had mentioned maybe you were looking into using SDL, and was it with you I was saying maybe you just want to look at what I did? I don't know if you ever ended up doing that. Okay, so this is the IRQ handler. You're using an audio cue instead of callbacks. Is that are you using SDL? Is that like another way to do it with SDL? Because I thought the only way was with callbacks, unless maybe I just misunderstood. RTI. Okay, so there's like some way to just build a queue and add samples to it. Because the way I had understood it was you had to register a callback, and then you would get called back to feed this buffer. Which is what I'm doing. Okay, so here's the thing, right? So if in Bedlam we have this interrupt handler, and you see it's pretty long actually, right? Yeah, it's really long. Okay, actually we can see it here. It's all this code. No, yeah, until this place here. Wow. Oh, okay. So the SDL offers a different interface, and then they take care of doing the callback stuff for you. That's pretty cool. I didn't even know it could do that. It sounds pretty nice. I mean, in effect, I suppose the interface that I'm exposing to my SDL audio driver is kind of that. You just give it a vector of samples, and it does the thing. Or I think I have like an add sample function or whatever. And you can think of it as just adding those to the queue, and they do eventually get processed in the callback. Okay. So was it cool, like writing the emulation of the audio chips for the Game Boy? I find it really cool doing that kind of stuff. So here's the thing, right? So before the IRQ handler, you can see that I is low over here, and actually this instruction that you see at F19E, in my trace I'm showing it as if we're executing it, but we're actually not. It's at this moment, in fact, that we're about to enter interrupt handler. So this is more of like I should probably improve my trace to detect that we're about to do an interrupt handler here, and not show this here and just say like, executing IRQ. And because actually all the stuff you see here, this is the pushing on the stack, right? You see all this here? We're pushing a bunch of values to the stack. See, the stack was at CBE6, and then we subtract and start pushing all these values. And then at the end, our flags register shows the final state, and at this moment I is 1 because we set I to 1 for the duration of the IRQ, which is down here. So from now on I is high. Right. It's so cool though, right? When you start to hear like the bits of music that you recognize. I remember it was so exciting when I was writing the sound code for the NES emulator, and I was using Mario 3 as my test ROM for that, and it was just so cool to hear. Or actually, it was Mario 1, I think. I don't know. Anyway, one of the Marios, and just hearing the classic songs, it's like, wow, it's awesome. Okay, so I remains high throughout the entire IRQ handler, of course, and then when we return from interrupt, we pop everything, including the previous state of I, and when we're done, I goes back to being low. Only problem is the channel is always enabled, so it outputs junk when nothing is being played. Right. Right. And that'll be mostly, like you said, doing the sweep or enveloping, right? So probably once you have the volume envelope in there, it'll kind of fade out sounds, and then you won't hear that anymore. Okay, so I is low, where formerly it was high, and we were okay. So what then next causes a problem is probably another IRQ handler. And no results, really. Oh wait. Oh, there we go. The dollar sign was okay, because I was in regex mode, so that was taking that as end of line. Okay, so here, this is where we end up getting another interrupt here. So it's one of two things that I'm thinking. Yeah, so there's two parts, right, to the interrupt. Where does the game set I to 0? So that's one thing we can figure out. And the other thing is, whoops, yeah. Where does the game set up which interrupt in the to wait on? Where does the game set up, and which one is it? Those audio terms sound scary. Oh, you mean like the envelope and the sweep and all that stuff? Man, I had like no idea about audio when I first wrote my NES emulator, like zero. It was all new to me. And I've said this so many times on stream, but honestly, the first time I did audio in my first emulator, I think it took me as much time to implement it as it took the rest of the emulator up to that point. I had the CPU and I had the graphics working, I had input working, and it was great. And then I was like, okay, time for audio, and I spent so much time doing audio, and I thought a lot about it, and I think it's because there was also the complete lack of experience, and I first had to learn how to deal with SDL and the buffers, and I was having problems with starvation, starving the buffer and all that. There's a whole bunch of stuff there. Then there was like learning about how audio works and just understanding the terminology. And then another big part of it is I spent an enormous amount of time trying to get it to sound perfect. And what I mean by that is, there's a big difference with like between, let's say, not getting the graphics quite right, but it being just good enough, and not getting the sound quite right. Like, for example, maybe, my palette wasn't perfect, or maybe if I had a small bug in the palette and it's, the colors are slightly off, I wouldn't even notice, But when it comes to audio, you notice every slight imperfection. It's like one of the, least forgiving aspects, right? If one of the chips is slightly off, you'll hear it. If you are not able to produce samples fast enough, you'll hear it. You'll hear clicks and pops. So it's really, really annoying, and it's also really difficult to track down, to debug. So I think that's where most of my time went. For the Vectrex emulator, it went a lot faster because it wasn't my first time, and I was able to reuse my SDL audio driver. Plus, it's a simpler chip. But if you guys were watching my stream, I did spend a lot of time, debugging and trying to clean it up and figure it out. It is brutal. One thing I can say though is if you have any kind of visualization, like this time I used ImGUI to help, right, to draw graphs and stuff, and I found that to be quite helpful. And most of the old systems output the sound at like 4 megahertz. Yes, that is true. Which is actually a good thing, to be honest, because it means that you can like just do simple sampling. You don't really have to do any complex resampling. For my emulator, I average, but even if you don't average, even if you just take the sample like at the target sampling rate, if you know that you're doing 44 kilohertz, every time you need a sample, you just go and check what's this, like you sample your thing, you'll be fine. Yeah, exactly. You're skipping the in-between samples until you need one, right? So what I'm trying to say is it's a good situation when the source sampling rate is higher than the target, if that makes sense. Saw a nice DSP Stack Exchange thread about audio decimation. Yeah, see that's where like my lack of signal processing, engineering, electrical engineering, all that really starts to show. I don't really know a lot about that kind of stuff. I kind of get it, like a little bit, but yeah, I'm not. I didn't really learn that, I did computer science and didn't really do much hardware or any kind of signal processing or anything. But yeah, sounds, I do wonder like what a difference it actually makes at these frequencies and stuff. But anyway, I don't know. Enable. And possibly it's accessing the interrupt flags, but it's more interrupt enable that I want to look at. Well, definitely keep me in the loop, Michael C. And if you have code or, if you want to share anything, let me know. This is the one, via int enable. Cool. No, it's so yeah, there's quite a lot of these. Okay. No results for int enable. So let's see. How can I answer these questions? Let's modify our CPU code to try and detect when I becomes 0. So I'm just going to run my emulator here. And okay, so here we go. So this is an instruction that has executed just now. I'm going to go my debugger. This is like my little trick. And then I set my break into debugger to true so that when I hit F5, I'm broken into the debugger right after that instruction. And then I can actually just take a look. Oh yeah, it uses CWAI. So this must be, maybe that's where I've gone wrong. It's the way CWAI works. This game uses this instruction. So this is a weird instruction. I think it's weird. It's the one that says, I want you to stop and wait for an interrupt. And I wonder if my bug has to do with, I'm just going to leave this like this. See, there's another op CWAI. This just keeps getting called. So we wait. I'm guessing that when we are done with this, we're supposed to put the mask back to 1. Is that possible? That's probably how it's supposed to work. Let me see. But this does set it back to 1. Wait, op CWAI. What does this do again? Oh yeah, we pushed a CC state here. So maybe what we're supposed to do Let me read about it. I wonder if it's around here. Clear CC bits and wait for interrupt. This instruction ends an immediate byte with the condition code register, which may clear the interrupt mask bits I and F. Stacks the entire machine state on the hardware stack, and then looks for an interrupt. When a non-mass interrupt occurs, no further machine state information need be saved before vectoring to the interrupt handling routine. This instruction replaces the M6800 CLI WAI sequence, but does not place the buses in a high impedance state. A fast interrupt request may enter its interrupt handler with its entire machine state saved. The RTI instruction will automatically return the entire state after testing the E bit of the recovered condition code register. So it looks like I'm doing what it says. So, you know, I read the operand, the immediate operand. I AND it against the condition code register, and basically they're saying that the values that you should expect should be one of these four: FF, EF, BF, or AF, because these are the bit masks that would toggle or not toggle the IRQ or the FIRQ, so the I and F fields. Although enable neither would seem kind of strange. Why would you wait for an interrupt but not enable either of them? I guess that wouldn't make much sense, but you'd probably do either one of these three. Okay, so that's this book here. Let me see, I have a few more just to double check. It doesn't say very much. This cycle one was always kind of interesting. That didn't work. Okay, opcode fetch, mask, don't care, PC low, PC high. Opcode fetch, then we do the masking, and then we push everything to the stack. Because I guess what I'm trying to figure out is, what if we mask? I mean, everything points to the fact that we're supposed to store the result of the mask directly into CC right away, and then when we push the state, that's what gets pushed, right? But maybe what we really want is to push the state, then do the masking, so that when we come back, it restores the state to how it was previously. And if I did that, maybe it would make more sense. Let me just see. So that worked. See, so that works because, and maybe it makes no sense, because basically after the interrupt handler returns, it will pop the state and bring it back to exactly what it was before we called CWAI, which seems logical to me. But see, when you read, when you read what's written, that's not what it says. You know what I mean? It says, this instruction ANDs an immediate byte with the condition code register, which may clear the interrupt mask, comma, stacks the entire machine state on the hardware stack, which includes the CC register, which includes the flags register, and then looks for an interrupt. So if you read that, this is what I did here is not exactly what it said, right? I'm pushing the state, then doing the masking, and then waiting, and then, But see, if I do it this way, it works. So let me try and see. And I was looking here. Here it doesn't really tell us anything. It just says CC mask. So this tells us something. It says the mask happens on the second cycle. But maybe it doesn't get. Yeah. See, like I'm just not convinced that what I did is right. It seems to imply that this is what we want. The opcode fetch is this. CC mask would be this. And then the rest here, well, there's a couple of cycles that nothing happens. And then it's push the PC, the user stack, the Y, X, DP, BA, CC. And this CC would ostensibly contain the change that comes from the mask. Right? And then after that, it says here we wait, do while interrupt not present. And then when the interrupt is present, we proceed with jumping to the interrupt. So we read the high and low addresses of the interrupt of the IRQ vector. So anyway, if I do this, it works, but is it again working for the wrong reason? So let's see if I can find some more information. I'll go back to this one here. Hello? Okay. This says pretty much the same thing. Starts with logically ANDs a byte of immediate data with the condition code register, which would mean it would store it in the CCR. Usually enabling the regular or fast interrupts saves all the user registers in the hardware stack. So once again, does it afterwards. Cycles for execution of CWAI. They're just showing examples. Logically ANDs the condition code register with the following byte of the immediate data before halting instruction execution. Logically ANDing the condition code register with this clears bit 4 of the condition code register, thus enabling the regular interrupt. Similarly, logically ANDing with this would clear bit 6, thus enabling the fast interrupt. Logically ANDing with that would enable both mask interrupts. CWA causes 6809 to save all its registers to the hardware stack and wait for an interrupt to occur. In response to an interrupt, the CPU disables IRQ and transfers control to the address in memory locations. Remember that all the registers have already been saved. The service routine clears the startup interrupt. It's not the same thing. The service routine clears the startup interrupt by reading the appropriate PIA. This operation is necessary even though no data transfer is required, otherwise the startup interrupt would remain active and would interrupt again as soon as the CPU interrupt was re-enabled. So that's right. RTI restores all the user registers from the hardware stack, thus re-enabling the CPU interrupt since the old flag is restored. Wait. Wait a minute. Am I reading this right? So if I'm reading this right, it is saying that RTI, because it pops all the, it restores all the registers, the interrupt would be enabled. The one that got set by masking, with like by anding with the mask. Oh, I don't understand then. What the hell? It is that. You see, like it says, for example, it says here, logically ANDing the condition code register with this clears bit 4, thus enabling the regular interrupt. And then it says, CWAI causes the CPU to save all its registers. And then it goes, in response to an interrupt later on, the CPU disables IRQ and transfers control. And then later it says, in response, the CPU disables IRQ, transfer control. Remember, all the registers have been saved. Okay, and then the disable routine, and then RTI restores all the user registers from the hardware stack, thus re-enabling the CPU interrupt. Since the old flag is restored, the flag that was pushed to the thing. So yeah, what I was doing is correct, but it doesn't fix Bedlam for me. I mean, it keeps Bedlam broken, as is. It means that probably, okay, so maybe I'll focus on the other question, which is the question of what is the interrupt that is causing us to, like what is the interrupt coming from? Because that's one thing I don't have an easy way of tracking right now, is which thing made the interrupt. Like, it would be really, really useful to know. Sorry, I'm not very clear right now. What I mean is, see, all I know on the CPU side is some flag, bool, IRQ enabled. But actually, the IRQ being enabled, it's rather complex. What causes it to happen is in here, we ask the VIA if IRQ is enabled. And in there, it's complex, as you can see, because what we do is we have to check if any of the bits of the IRQ enabled flag are on in the interrupt, in the IFR. So the interrupt flag register. And so far, what my emulator supports, and I think it's, if it didn't support, yeah, there's a few that I don't support, but if any game or ROM attempted to set these, I would catch it with this assertion here. So far, that's not the case. So what I support is enabling the interrupt to occur for the CA1, for the shift register. So whenever it completes its cycle, it can generate an interrupt, for timer 2 and for timer 1. This is some old code that doesn't belong here. RQ if any IFR bits are also enabled in IER. Okay, get into flag value, and then why are we doing this here? Test the bits against. This seems strange. Since we're already doing this here. The bits in the result using IRQ enabled as a mask. And we turn on those bits if the result and the interrupt enable are also the same. Sure. So it seems to me this test bits is not really required. I could just check if this flag value is non-zero. I don't think this will change anything, but yeah. But let's see that it doesn't change anything. Oh, no, it does. Fascinating. What? Oh yeah, I guess not exactly the same. Let me see here. wait. Okay, of course. I see. There's one bit in here called IRQ. Let's try it. That's it. That's how it works. It's coming back to me now. Yeah, so this bit automatically gets enabled if any of these are on and that bit is also on in the interrupt enable register. So basically it's like, you know, if we enabled interrupts on shift and shift happens to be enabled, then this guy gets enabled. And that's what we're doing here. So we're enabling the IRQ bit if any of the IFR flag bits, which have been set above, are also enabled in the IER. And then IRQ is enabled if that one bit is enabled. Okay. So then the question is, which thing caused the IRQ to occur? And that would be really, really interesting to know. We have this IRQ enabled here, but it would be nice to know what was the reason? I'm trying to think how I could communicate that easily. Suppose I could read the interrupt flag value from the VIA. But I'd have to do the same ANDing I'm doing here. But I have access to both of those. So I could read interrupt flag, read interrupt enable. Maybe I should just ask the VIA to tell me. And in fact, we only want to know if we actually handle the interrupt. That's the thing, which is also kind of annoying. Because that happens all the way over here in the CPU. There is something we could do maybe, but it would mean splitting out execute instruction into two things. I was going to say maybe we would want to do like execute instruction and another function called handle interrupts, which could return whether or not it handled them. So I'm trying to figure out, because it would be super useful for debugging if I could say what caused an interrupt, right? Just in general. Okay, let me see. So it's always the case, if this is 0 and VIA would return this, we are going to handle an interrupt. So it would be nice here to print that. I think it's not an op, but anyway, for now, let's try something. I have to move this into the header file. Or maybe we can just do something dumb and just say like, finished implementing enveloping. Sound only runs when it's supposed to now. Nice. Good job, man. That's awesome. He must be so happy. Oh, is it private? I might have made it private. Yeah, so those two. Yeah, you can bear to listen to it. And I'll add this in there, not equal to 0. No, it's not a flag we want. We just want the mask. So yeah, it'll be interesting to see how this works. No? Why doesn't it want this? All right. Yeah, it did not work because I did not actually use the right address. Try again. So if I just wait long enough, we do hit this. IFR and IER. Interesting. So we are waiting for quite a few to be on. It's got optimized out. And then we print. Oh, we should actually not print. We should error F here. If I actually want to see it. So it says 44. Does that make sense? Mm-hmm. It does. So shift is enabled. Is that timer 1? Timer 1. Okay. Oh yeah, and I forgot to put a new line. So I have a feeling I don't know. Let's just see. Okay, so see, we just, while we were running, we were constantly getting interrupted. I bet you we were not supposed to be interrupted by the, but I guess they enabled it for the shift register, so Yeah, there's a part of me that really suspects that my shift register enabling stuff is completely not correct. I don't know if it's going to affect this, but let's see. Yeah, because I always return true. I wonder, why is the game even checking for that enable bit? But then see, when we hit go, I should have written this down. This one calls CWAI. After that, I remains 0 when it returns an interrupt. So here's a question. So I was able to fix this by swapping the order of when my interrupt mask gets set, so that when we return, it goes back to 1 and does not remain 0. And then everything worked. And I wondered, does it mean that the code then later on calls CWAI at the right moment, and that's why it works? And that right now we're getting bogged down by an ISR that's being called at the wrong moment. That's what I suspect. What was it again? Oh, hey, Douglas Drums. Thanks for the follow. Appreciate it. C with immediate value to set I to 0. After pushing CC stack, then then RTI would pop back CC with I equal to 1. This works, but is probably not the correct fix. It works because the game then waits until it calls CWAI again to start handling interrupts. What doesn't work right now, what doesn't work is that upon RTI, I is 0, so it just keeps going into the IRQ handler. Because shift register is enabled. We know why. We see it because both shift register and T1 interrupts are enabled. This is my form of rubber ducking. I'm writing out what I understand, and as I do it, it forces me to think about whether what I'm thinking makes any sense. So like here I'm wondering, we come back, and then do we immediately break? Up RTI. So here we are. We just did an RTI. Let's step. Step. So here we are, we're stepping, and we're not going to get an interrupt. Why is that? So interrupt mask is indeed 0, but IRQ enabled is not true? It's not. That's interesting. Hey, Douglas Drums. Nice, I do that sometimes, not exactly as rubber ducking. I use it as a stack trace of my thoughts, so when I'm interrupted, I get back to work quicker. Oh yeah, absolutely. That's another, yeah, that's another reason why I write down my thoughts. I am looking at the time and thinking I probably won't finish this, but I don't want to lose any of this context. So yeah, that's definitely another reason. But it's also helping me to work through this jumble of thoughts right now in my head until like it forces me to ask myself, what is it exactly that I'm looking for? So at the moment, shift register and the other one are not enabled. But then when it does happen, it's like as if both were enabled, which leads me to believe, okay, so let's go a little bit deeper here. So why isn't this happening? Let me go and step into here. Oh, and I just messed up my stack. Great. That's a risk of moving the IP sometimes. It's okay, we can get back there. Okay. And say go, and there we are. See, like I find it interesting, we're getting the exact same interrupts enable mask when we finally get through, but what I want to see is if I put a breakpoint again on this, so we're returning from our interrupt routine, and then we start stepping. We come back in here. No, in here. Where are we? Step. Let's see. So C1A is not on. This one, of course, will return true. So yeah, so what's telling me is that the interrupt enable flag, this is the one that's important, I think. Yeah, you see it has only a bit set for interrupt enable. Sorry, for timer 1, I believe. Yeah. Yeah, is that true? Or is that timer 2? 0, 1, 2, 3, 4, 5. Timer 2, actually. Right. Yeah, this is timer 2 is the, yeah, okay. Because we are right now, comes from the BIOS. The BIOS is doing this. It wants to check the interrupt flags. It's polling the interrupt flags. So you see, to me, this just tells me I should be 1 here. We should not be able to capture this. So why is, like, what is supposed to set I to 1? That's the big question. So okay, let me just take this note. But one thing I don't understand is that the reason we print that we ended up going back into the interrupt handler is because of shift register and timer 1. which means that somewhere we're modifying the interrupt enable flag, right? No? Yes? No? Yeah, it must be that. It must be that the interrupt enable is getting set. Put a breakpoint here. And hit a 5. Where are we? RTI. No, so we don't get a change in interrupt. So now I don't understand. Let me check again. We step. Yeah, we're looking for timer 2 right now. Okay. But at one point, this here will become true. Now, when it became true, what did this look like? The interrupt enable value. Still 32. Getting back 32 here. Did I put in the wrong thing? Oh, such an idiot. Okay. Okay. Yes, I actually had checked this before. It was the, oh my goodness. All right. It would be helpful if we actually had real values in there. Okay, so this might actually help clarify things. So what's the deal here? Okay. Okay, so now we're saying because of 20. So is that timer 1? Timer 1, timer 2. Yeah, I believe so. Timer, oh, actually, no, timer 2. Yeah, still timer 2. Okay, So we're waiting on timer 2. Okay. So here we are. We're about to start the game. I think what's going to happen is that right now, yeah, I is low. And as soon as we hit start, we're going to end up handling this routine before we're supposed to. Like we're going to end up handling the IRQ when in fact the VIA wants to do its clear, I think. All right, Michael C. Thanks for hanging out, and good luck on your Game Boy emulator. Looking forward to hearing more about it. Okay, so let me just see if I'm right. Let's continue. Yeah, so it's the same thing. And I think what's happening really is that we happen to be waiting on this timer just like the Vectrex's normal wait for recalibration function waits for it. It's also looking for this specific interrupt. So basically we've got the VIA that wants to poll for this timer, and we are waiting for this timer to occur. And it's all because that I flag is still enabled. So what is supposed to disable it? Okay, I'm gonna write down what I just figured out. Because instead, this also happens to be the flag that wait for recal BIOS routine is polling at the same time. Clearly, I should be 1 or set to 1 after RTI, so that wait for recal can do its work, and eventually the game code will call CWAI again when it's ready to process its interrupt, the T2 interrupt. So how is I supposed to be set to 1 if CWAI's RTI ends up restoring it to 0. So that's the question, isn't it? So what we could do, I think that what would help is we fix the game and then we look at what actually happens in between the time we want to start a match and we start playing it. Do we see anything? No, that's it. I don't suspect we'll see anything that turns I to 0 or anything that should turn I to 0, because that's what the CWAI code will do. Like, just logically thinking about it, right? We've got this instruction. This instruction says clear CC bits and wait for interrupt. So you want to call this because you want to wait for an interrupt. But after the interrupt service routine is over, you don't want those bits cleared. You want to be able to opt into it again, not have it remain. But you see, it says here, first thing is CCR gets the result of the current CCR and MI, which possibly clears masks. Set E pushes everything, including CCR. So if it cleared it, it would be restored cleared. Which means that as a programmer, you'd have to somehow unclear that if you don't want to receive them anymore, these interrupts. I don't see how that makes sense. Let's try another. Let's try the cookbook. Why isn't this working? Find is not working anymore. That's great. What's up, Nook? So if we assume that this is correct, then I'm not sure. I'm not sure what else could be, how it's supposed to be handled. The only thing I can think is maybe there should have been like an op reset or something like that. Like maybe when the game is over and we return to the title screen, there's supposed to be something that runs that would want to set I back to 0 explicitly. Sorry, I set I back to 1 explicitly. But I have not seen any reset call or anything when I played this game. There is an op reset, but I don't believe, I don't know. You see, I have a breakpoint on it. See, we never actually hit it. Okay, that's interesting. So during gameplay, the interrupt mask did become 1. So let's see what turns it. That's interesting. So what is it that makes it go back to 1? Oh, of course. The CWAI instruction did that. But I mean, that's probably the only thing, right? (09B9) CPU opcodes. Wait, oh no, that's just a PC. It's not the instruction. How do I maybe I'll hard code this. It's always going to be that, right? 09B909. Oh, there's a few different addresses. Oh, no, that's right. It's 09B9 when it first becomes like that. Then after that, it remains 1. So I want to detect more like the edge when it went from 0 to 1 due to the instruction. But that'll only certainly be because of CWAI. Okay, so what I expect is that we'll get CWAI and then RTI. Here. So yeah, CWAI is when it became 0. Oh, and we have a jump. That makes sense? How could that be? Or is it that we processed RTI and we are now at jump at the end? That's possible. Oh, there's RTI. Oh, interesting. Jump. RTI. Jump. How could jump change the mask? RTI makes it 0. And then this jump call made it 1. I think this jump, let me see, debugger, break. Okay, it's just saying jump, but it was actually CWAI. Right, because when we execute CWAI, we actually don't make it to here. Because what happens is we're waiting for an interrupt, so we just end up returning. And then as soon as the next instruction, which is the jump, runs, then we're good. Okay, so at least that makes sense. right. Okay. Okay, then RTI. Okay, so I've documented what I can here. I'll save this in my Vectrex stuff. Bedlam notes. There is still this question, right? Like, does Bedlam actually set the interrupt enable directly? It doesn't look like it, right? We know that that's a confusing thing. We know that the BIOS sets it when it's doing wait for recal. In fact, does it even set? No, it doesn't set interrupt enable. It just reads the flags. Yeah, that's right. Okay, so let's go into the VIA here and look for interrupt enable. Start all over. I'm curious to see if the game sets interrupt enable. Okay, so we've got a write early on, but this is even before we've started. So what's this again? And actually, wait, maybe it's just setting it to 0. No, we've got a value. Wait, oh, yeah, this is always a complicated one. Oh, okay, that's it. It's disabling all the bits. Aha! So here's the call that enables the T1. So this actually was an important question we need to answer. The game does this. Let me see. See, there, here we are in the game code. And after that, continue. Oh ho! So there is a write. What does it want to do? It wants to disable the interrupts here. So it's trying to set 0 and then all 1. Let me see where we are when this happens. When we die, when we are game over, and we press 1 to go back to the start menu, interrupt via int enable gets cleared here. So again, we're still in game code. So here we can see that we're trying to write 7F. That's a clear. So now the thing is, if it's clear, okay, no, that's fine. But there's a question of, wouldn't we want, see here I is low, and that's the problem, right? It's going to remain low. Like the next time we run this code, I will already be low, if we even get to this code, which we may not even get a chance to. If I hit, okay, we did get a chance. Let's just see what this state looks like. Hey, Bama. Cannot say much. Well, thanks for joining anyway. Start next game. This is where it enables. Oh wait, press button for start playing, and and T2 interrupts interrupt is enabled here. Start next game. T2 interrupt is once again enabled here. But this time I is So there are a few minor differences here between the first and the second call. Interestingly, the entire flag is still set, which I think is okay, because that happened where over here we had not yet done a CWAI, and here we had, and when we did, it ended up setting entire to on, and then entire doesn't really matter until like the next time we push things on the stack, so that's okay. Interestingly, I guess the main thing I was always pointing out is that I is now 0, so interrupts are always enabled at this point, which is wrong as far as I'm concerned. Which oh yes, Brahim, that's right. This helps you track issues. Which one? You mean beyond compare or just writing down my notes? Notes, yeah, definitely. Definitely. Like after this, or I'll put this here, or I'll say after this, we'll end up running the game's IRQ handler when the BIOS is waiting. Wait for recal. As described above. All right, so guys, I am going to stop here because it's late and I'm tired, but we made some good progress. And I think, you know, if I think on this a little bit, maybe it'll come to me in the shower or something. So, you know what? I was thinking of trying something I've never tried up till now, which is, if you guys are cool with that, look for someone to raid. I have a bunch of programmers that I follow. So let me take a look if I can find someone. Let's see, is there any programmers right now? Oh, hey, look, it's me. Or maybe not. Everyone's offline. Oh, so much for that. Maybe next time. So everyone, thanks for watching. Hopefully next time we will make more progress on this and solve this problem with Bedlam. So yeah, thanks for watching and see you next time.